Okay, so we're going to take a look at the perimeters and areas of similar figures. This is a two-page activity at the beginning of the 11K notes. And from this activity, what we're trying to get is that there are some relationships between ratios of these shapes and things like that. So we'll just kind of figure these out as we go. The first thing you're going to need to do is read the directions. The similarity ratio up at the top, it's defined for you. It says it's the ratio of the corresponding dimensions of two similar figures. And then the directions say that all of the following figures are similar. So you need to notice that all of the following figures are similar. Find the perimeter and area of each of the following figures, then fill out the chart and answer the questions below. So the beginning is just very simple plug and chug kind of math stuff where we have to figure out the perimeter and area of each shape. I already have that done. If you want to take a minute, pause the video, find the perimeter and area of each shape, and then come back to the video and it'll be filled in. For those that aren't pausing and are just waiting to copy, proceed now. The perimeter of the first one is 24. The area is also 24. The perimeter of the second one is 12, and the area is 6. Here it's 12 and 8, and this is 36 and 18. Okay, so we've just answered those questions. If you go down to figure 3, again, if you want to do this on your own just to practice perimeter and area, feel free to pause the video right here. Get some answers for yourself, and then come back to the video when you're done. The first one has a perimeter of 56 and an area of 108. And I'm just using base times height for area of a parallelogram. This is 28 and 27. 50 and 60 over here, and then 25 and 30. Okay, so now we're going to fill in this chart. Just answering the questions. So if you look at the right triangle, so that's back up at the top, the right triangle, the very first one, figure 1. What's the ratio of the width? Well, depending on which one's width or base and height, we use different terms. But if you just look at the ratio of two of the dimensions of the right triangle, we'll say 6 to 3. So the ratio there would be 2 to 1. The ratio of the length, if we look at the other dimension, it would be 8 to 4. So the rate, if we reduce that, remember ratios are often thought of as fractions, we can reduce 8 to 4, and that's also 2 to 1. The ratio of the perimeter, well, that's 24 right here to 12 right here. Well, 24 to 12 reduces also to 2 to 1. And the ratio of the area. The ratio of the area is 24 to 6, which reduces to 4 to 1. Okay, so that's the first line of the table. Take a second and see if you can fill in the rest of the ratios. Pause the video if you'd like right here so you can practice putting those ratios in, and then unpause it when you've completed that. Okay, so I have all my ratios in. There was an error. I apologize. I copied something wrong up here. The perimeter of that rectangle is 18. Sorry about that. So down at the bottom now, I filled in the table just by setting up fractions and then reducing them as ratios. And then I'm going to try and answer these questions. It says, number 1 says to compare the ratios of the perimeter to the ratio of the sides of the figure above. And what do you notice? Well, what do you notice? The ratios of the perimeter to the ratios of the sides, so the width and length, or the base and the height. And what do you notice? Well, what you should notice is that they are all the same. They are the same. Okay. Compare the ratios of the sides of the figures to the ratios of the areas. And what do you notice? Well, let's take a look. What do you notice about the ratios of the sides compared to the ratios of the areas? Well, for example, the right triangle is 2 to 1, okay? And then the ratio of the area is 4 to 1. In the rectangle, it's 2 to 3, and the ratio of the area is 4 to 9. So what do you notice? Well, what you should notice is that the ratio of the area is the ratio of the sides squared. The ratio of the area is the ratio of the sides squared. Make that a little smaller so it fits for you. Okay. Now let's take a look at the theorem at the bottom. If the similarity ratio of two similar figures is A to B, then the ratio of their perimeters is, well, that's also going to be A to B. The perimeter ratio and the ratio of those lengths each time was exactly the same. So that's also going to be A to B. And the ratio of their areas, well, what would the ratio of their areas be? What would the ratio of their areas be? I'll give you a second to think about that. I'm going to pause the video for just a second. If you want to think of it, let's just do this. Let's just tell you the answer. And rather than mess with, there we go. The ratio there would be A squared to B. Easy. To B squared. So this one's A to B, and that one's A to B squared. All right. Those are the similarity ratios that we're going to work with perimeter and area. Let's take a look at the next page. Here we're looking at area and volume of similar solids. So similarly here, we're going to compare area and volume and see what we get. Now I will tell you this is slightly more complicated because we're going to have to reduce some larger fractions, and you're going to have to know how to either reduce the fractions or to use your calculator to get some answers here. We've calculated the area and the volume for you each time, so you don't have to do that. That's all right here for you. But we are going to have to come up with the ratios. So I have my calculator up right here, and we're going to calculate some ratios. So the ratios of the sides, that we can probably do. For the prism, we go from 60, 40, and 30 to 24, 16, and 12. So I'll just do the two largest. That's I can set that up as a fraction as 60 over 24. Some of you may be doing it in your head. And getting 5 to 2. So I'm going to put 5 to 2. The ratio of the area. Well, the ratio of the area of each, is 10,800 and 1728. So on my calculator, I'm just going to take 10,800. The fraction button is A, B, C, that button right there. And then put 1728 as the denominator. I hit enter and it reduces it for me, and that's 25 to 4. And then the ratio of the volumes, that's 72,000 and 4,608. So 72,000, not divided, excuse me, and then 4608. And I reduce that and I get 125 over 8. So 125 to 8. That's an 8. Take a second, pause the video, and then see if you can calculate the ratios for this cylinder. Pause the video and go ahead and work on that, and resume the video when you're done. Okay, so I've calculated those. I set up the fractions each time and reduced them and got my ratios 9 to 7, 81 to 49, and 729 to 343. Compare the ratio of the areas of the solid figures to the ratio of the sides. So area to sides, and what do you notice? Well, we should notice the same exact thing that we had on the page before, and that is that their ratios, the ratio of the area is the ratio of the sides squared. Area is ratio of the sides squared. Now it asks us to compare the ratio of the volumes of the solid figures to the ratio of the sides. So not volume to area, but volume to sides. So let's compare those. We have 5 to 2, okay, the ratio of 5 to, and a ratio of 125 and 8. Well, what we should notice, and some of us notice this quicker than others, so I'll help you out a little bit, is that if we take 5 and we multiply it by itself 3 times, or cube it, 5 cubed is 125. Okay, 5 cubed is 125. Well, what is 2 cubed? 2 cubed is 8. So what I should notice here is that the volume ratio is the sides, let's word that a little bit differently, is the ratio of the sides cubed. Okay, and then here the theorem at the bottom: if the similarity ratio of two similar solids is a to b, then the ratio of their corresponding areas is a squared to b squared, and the ratio of their corresponding volumes is a cubed to b cubed. This activity will help you understand the rest of the Notes 11K. You may be doing this in class or Flex, or you may be asked to do it on your own, so it's its own video. Enjoy!